Rank the following statements in decreasing order of likelihood. Okay, so what I want you to do is to generate. The story is Linda is 30. Okay, she's a single woman with an advanced degree. While at college, she was active in protesting against nuclear power. Okay, that's the story. Okay, I want to see how well you understand this story. Okay, by taking the following 8 statements of Linda about Linda and rank them in order of most from most likely to least likely. So I want you to generate a permutation of the numbers from 1 to 8, ranking these from most to least likely. Okay? So how likely is it? Think about it. Is it more likely that Linda has blonde hair or dark hair? Is it more likely Linda is a feminist? Okay? Is it more likely that Linda works as a bank teller? Okay, or works in management? Okay? Is it likely that Linda, where does it rank that for the likelihood that Linda is both a bank teller and a feminist? Is both blonde and a bank teller, and both blonde and in management? So I want you to go and write down a permutation of the numbers 1 through 8, ranking statements in order from most likely to least likely. Do it now. This is an exercise in probability. Okay? Okay, so just on your own sheet of paper, give me a rank, write down the numbers from 1 to 8 in order from most likely to least likely. Okay, I want to give people about a minute to do this. Okay? And, you know, this is not on the exam, but it's a test now. Okay? It's a test of how well you understand probability. Okay? So, again, what I want you to do is to rank, to read the story. Linda's 30. She's a single woman with an advanced degree. While at college, she was active in protesting against nuclear power. Okay? What I want you to do is to now rank the following 8 statements in order from 1 to 8, most likely to least likely. So you should give me a permutation of the numbers from 1 to 8 corresponding to how likely these statements are. Okay, so from most likely to least likely. Okay, and when you're done, raise your hand, just so I know how many people have it sort of done. Okay, this is a little exercise. Okay, so I do want people to think about this quickly. Okay, so the statements are, number 1, Linda has blonde hair. Okay, we know what we know about Linda. Okay, is it more likely that Linda has blonde hair or dark hair? Is it more likely, how does that compare to the odds that Linda is a feminist? Okay, how does that correspond to Linda being, likelihood of Linda being a bank teller, Linda being working in management, Linda being both a bank teller and a feminist, Linda being both a blonde and a bank teller, and Linda being both blonde and in management. Okay? Rank these statements from most to least likely. Okay? And when you have that a ranking down, raise your hand. Okay? I want people to think about this for just a little bit. I don't want to waste the whole class on it, but I do want people to go through this exercise. Okay? Okay? So, how many people have their ordering? One person sort of has ordering. Let's give it another, I'm going to give it 2 clock minutes now. Okay? So for those of you who come in later, haven't seen it yet, I want you to order these statements. Give me an ordering of the numbers 1 through 8 from most likely to least likely in terms of how likely these statements are true, okay, or false, okay? One says that Linda, the story we know about Linda is that she's 30, she's single, she's smart, she has a degree, advanced degree. While in college, she was active, politically active, okay, in protesting against nuclear power. That's what I will tell you is true about Linda. I want you to now, based on this, organize the following statements about Linda in terms of most likely to least likely. Okay? let's think about that. How many people have their orderings? Okay, 2 people. Let's give it a little bit, think a little bit more. So rank these statements from 1 to 8. And it will give you literally 1 more minute. Okay, when the clock hits 2:27, I will stop. Okay. 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 That's good. Okay. How many people have their orderings from 1 to 8? Okay, a bunch of people. Okay. Let's now look at these orderings. So now hopefully people have, at least people came on time, have ranked these statements from most likely to least likely. Okay? The question I have for you is, so there's some permutations that are illegal, okay, that people may have put down in terms of most likely to least likely. Okay? How many people felt that, let's say, the probability that, who feels that Linda, if you take a look at your permutation, how many people think Linda is more likely to be blonde than dark-haired? How many people think it's more likely that Linda is dark-haired than blonde? Okay, I can't tell you anything about hair color. I don't know that. But what I do want to ask you about is the following. Is there anybody here who wrote that statement 6 was more likely than statement 5? Is there anybody here who put down that statement 6 was more likely than statement 5? Okay? Some people wrote down that statement 6 was more likely than statement 5. Now I ask you, how could that be possible? Okay? Because it says, statement 6 says Linda is both a bank teller and a feminist. How can that be more likely than the fact that Linda is a bank teller? Because it's clear that if Linda, there are bank tellers who are not necessarily feminists, okay? So my claim is that if somebody, that somehow, this is the conjunction of 2 statements. This is one statement. The likelihood of these 2 things happening, by definition, has to be less than or equal to this. There is no way that the combined statement can be more likely to happen than the single statement. So I want you to now, do people see what I mean by that? Okay? Take a look at yourselves. How many of you, okay, picked one of these conjunctive statements as being more likely than, was there any one of these, how many of you put statements 6 through 8 as being more likely than any of these other statements? I mean, was it that you made some kind of a goof in your understanding? Okay? How many people will confess to having said that one of these is more likely than one of those? Okay? How many people won't confess to that? Okay, but did it anyway? How many people's logic was consistent enough that, that in fact these things with the conjunctions of statements were always less likely to occur than the single ones? Okay, a lot of people did that. What's interesting is that, again, you guys are relatively educated about probability and mathematics and reasoning. There's still some people who got it wrong here. When these kind of surveys were given to people, the public in general, okay, a very large percentage of people made mistakes, okay, in their reasoning like that. A lot of people don't know how to reason probabilistically, and this is sort of one of the examples of it that I always kind of like. But so anyway, something to think about. It's important to remember that conjunction of events is no more likely than the individual events. Can't be more likely than the individual events themselves. Any questions? Okay, what I'd like to do now is today talk a little bit more about 2 what I think are interesting problems in probability, related to sort of some of the probability things that we've talked about. I don't want to go through, I'm going to think, I'm not going to go through too much detail about some things like, well, we'll see, unless time permits, I'm going to try to avoid discussions of variance, okay, which is, while very important, many of you have probably seen before. I want to look at two different combinatorial problems and how probability might work into them, okay? One is a famous problem on computing sort of the number of derangements, okay? It has to do with talking about derangements. What is a derangement, okay? Suppose we have the story that we have a secretary, okay, who is given the job of taking n letters, which have been envelopes which have been addressed, okay, and n letters, which is supposed to go to a particular person. And that person is charged with stuffing one letter in each envelope. But suppose that instead of actually reading to make sure that the right letter goes in the right envelope, they randomly stuff letters into envelopes. Okay? What is the probability that none of the letters will end up where they're supposed to? Okay? There's a problem where somehow, basically it says that if I have n things, let's say like n people and n hats, you sometimes hear the problem talked like this. Each person has a hat. They go to a room to, their hats get mixed up and given back to them in random order. What's the probability that nobody gets their hat back? Okay? That's what I claim is what these problems of derangements. What is the probability if I have n people and I randomly give people, every person has a hat, and I randomly give hats to people? What is the probability that all of them get their hats back? Let's look at it this way. N people randomly assign this thing. What's the probability that all of them get their hats back? Okay. Can anyone see that? Okay. So now I have a world where, let's just make sure to warm us up on this problem. Suppose, let's say I have, 4 people. Okay, this guy's A, B, C, and D. Suppose I randomly scramble up, A gets hat 1, should get hat 1, 2, 3, and 4. I randomly scramble the numbers 1 through 4 and assign each person one of them. What's the likelihood that each one gets that everyone gets the right hat? Okay? So for n people, what's the likelihood that all of them got if we did a random assignment of things, that each of them got the one thing that they were supposed to get? 1 over n factorial. Okay? We agree that it's a very, very rare event that everybody gets exactly what they want. Why is it 1 over n factorial? Well, because there's n factorial. You can think of it as being we permute the hats that come back, okay? And only if we come up with one particular permutation, okay? If I think of the identity permutation, one of those permutations will give everybody back their hat. Otherwise, it doesn't. What is the probability that we have think about this, that exactly n minus 1 people get their hats back? Okay, suppose I randomly permute the thing. What is the probability? And everybody, I have the n hats, I scramble them up, I give everybody a random hat. What's the probability that all but one of them get the hat back? Okay. 0. Okay, there's no way only one of them can get the wrong hat. Okay, we agree with that one, right? So that you need to have at least, if one person's getting the wrong hat back, at least 2 people are getting the wrong hat back. Okay? Well, let's think of the problem where, that's the case where a lot of people get it right. What if, let's say, we want to think about how many hats, what's the probability that if I scramble, that nobody gets their hat back? Okay? Let's think of it now in the other direction. I now take n people, okay, if you want to think of it, and n things that they own. Scramble the things that they own. What is the probability that none of them get their hat, get what they own back? Okay, question.
I thought you were asking a question.
Okay, I'm asking a question. Okay.
N minus 1 factorial over n factorial?
The answer came back as n minus 1 factorial, 1 factorial over n factorial. which if that was true would be 1 out of n. Okay? So your claim would be that the probability would be that the probability that nobody got it back would be 1 out of n. I claim, in fact, that it's 1 over e, okay, where e is sort of 2.718, okay, dot, 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 okay? This is not obvious, okay, why this is true, okay, but it's kind of an amazing thing what it says. What it says actually is that if you have more and more people in the room, the probability that you end up getting, if somebody gets their hat back, doesn't really change. You might think that if you have a room full of, with 1 billion people, you scramble up the hats. Okay? It's more likely that somebody gets the thing right. But on the other hand, each hat can be scrambled over a lot more people. So the interesting thing, okay, what is that in fact this probability approaches a constant and stays there. Okay? And I'd like to show you a little bit how you might work this kind of thing out. Okay, a little bit more details about it. Okay, it's kind of an interesting and seemingly hard to believe thing. Okay? But what I'd like to do is the issue here, fundamentally, is I claim counting the number of derangements in a permutation. Okay? What is the number of derangements in a permutation? Well, a derangement, okay, the number of derangements of a given number, given n. A derangement is a permutation of n, okay, is a permutation of the numbers 1 through n, such that the ith element is not equal to I for any element. Okay, a derangement is a permutation where no element is where it should be. Okay, that's what we call a derangement. How many derangements are there of size, let's say n equals 2? Equals 2. How many derangements are there? 1. And what is that derangement? 2 comma 1. Okay? For n equals 3, how many derangements are there? Okay? 6. Well, what are they? Let's list some derangements. Okay? Why don't we try listing all the derangements that start with 1? How many derangements start with 1? None. How many derangements start with 2? Okay, if I have one that starts with 2, what's the next one that's going to be there? This is going to have to be a 3 and a 1. Right? I couldn't have, why isn't 2, 1, 3 is not going to work, is it? No. So if it starts with a 2, that's that. How many of them start with 3? If I start with 3, okay, what's the next one? 1, and the next one is 2. Okay? So I claim there's only 2 such derangements. Okay? Does everybody agree with that? Okay? How many derangements of n equals 4? 4 things are there. Let's think about that. How many derangements start with 1? None. Which derangements start with 2? Okay? I could have 2. The next one would be a 1. 4, 3. I can't have 3, 4, right? 2. I could have a 3 here. Now what are my choices? I could have a 4, 1, but I can't have a 1, 4. Hi there at Ademco. I noticed you guys just came in on the screen. Okay? We're talking, were you guys able to hear the lecture so far? Or nothing so far? Can't hear you at all. Okay. So you have not heard it? Hello?
No.
No evidence of that. Okay, I'm going to guess these guys didn't hear it. So let me just review quickly what we're trying to do. We're trying to count how many permutations of length n are there that no element is in its right spot. Okay? So they begin with 2. I claim that that's what 2, 3 would be like that. Is there anything that begins with 2, 4? I claim 3, 1, 3. Okay, right? How many derangements are there that begin with 3? Okay, I could have 3, 1, and then what? 4, 2. That won't, okay. Anything else that begins with 3, 1? No. 3, 2. What? I can't do that. 3, 3. Okay, no, that doesn't good. 3, 4. If I have 3, 4, what can I now do? 1, 2, and 2, 1, right? And finally for 4. 4, I could have 1, 2, 3. What other ones? 4, 1, not 3, 2. 3's in a bad place. 4, 2, that's not going to work. 4, 3, 1, 2, and 4, 3, 2, 1. So I claim that there's 9 of them here, 2 of them there, 1 of them there. Everybody agree? So how many derangements are there as a function of n? Okay? My claim is that that the trick to figuring out what the probability is, that there's no fixed points, okay? That actually is going to be the way that you would do that is you would count how many derangements there are and divide that by n factorial. Each assignment of hats is a random permutation. Some of them are going to be derangements, some of them are not going to be derangements. The ratio of those is the number of, the probability, correct? Here I claim is a recurrence relation to count the number of derangements, okay? And let's look at it, because it's kind of an interesting recurrence relation, okay? The claim here is that a d sub n is going to be equal to the number of derangements on n elements is n minus 1 times the number of derangements on n minus 1 elements, and n minus 1 plus n minus 1 times the number of derangements on n minus 2 elements. Why is that? Let's take a look at any derangement. Okay? If I look at any derangement, okay, on n things, if I have a derangement on n things, what do I know is in the n? What do I know about the nth spot in my derangement? What value is it? Or what value is it not? N. So we know that this is going to be some number k, okay, right? We know that somewhere else in the derangement, the element n has to be, right? Let's now think, what happens if we now swap this element with that element? Okay? By definition, it's not a derangement, right? But let's think what it is. How many fixed points will we have? A fixed point is an element in the right position. How many positions will we have if we swap this element with the element that was in the nth spot? Okay? We will have, there were none here, there's still going to be none here. Certainly the nth element is now going to create a fixed point. This element may or may not create a fixed point, depending upon whether or not this happened to be sitting in the kth element. Okay? If n was sitting in the kth element, then we would have it. If not, we didn't. Okay? So now let's describe all permute derangements of n, okay, in terms of what happens if you give me a derangement of size n. I claim that I can uniquely figure out which element do I swap with it, right? Okay, which element contains the nth spot. I could now think about performing that swap. The nth element could be in any spot from 1 to n minus 1, right? There's equally good many derangements of that. Okay? Once I know what element it is, I claim that I've got two possibilities. Okay? If in fact, when I do the swap, this element is not in its right position, that meant that after I did the swap, what I have here is a derangement of size n minus 1. Correct? If in fact that swap did not create a fixed point here, that meant that this meant that this had to be a derangement of size n minus 1. So how many derangements are there of length n that could be constructed that have the property that if you did that swap, okay, you did not end up creating any other fixed points? Well, we know that afterwards we had to have a derangement of size n minus 1. There's d of n minus 1 of those. Okay? And further, before the swap, n could have been sitting in any one of these positions. So I claim that there's a total of n minus 1 times d of n minus 1 places, okay, where, ways that we could have built a derangements of size n whose swaps do not create additional fixed points. How many people see what I mean by this? How many people are confused by what I'm saying? Okay, a couple people. Okay? Let's now look at the second part of the term. I claim that if we think of any derangement of size n, it comes in two different kinds of flavors. It meant that after we did this unique swap with it, either there were a total of 2 fixed points or there were 1 fixed point. We're going to count all the derangements in each category. The sum of them has to be the number of derangements in both. Okay, all told. Correct? So, if we created a fixed point here, let's think about it this way. Suppose, let's say that originally we had the element k was in the nth, that in the kth spot we had n, and in the nth spot we had k. When we did that swap, what did we have left? There were a total of n minus 2, I'm sorry about that, n minus 2 elements that were not involved with fixed points. Correct? Once we fixed the position of the swap, okay, the number of legal ways that we could have had permutations that ended like this meant that we had to have that if we were doing the swap in the kth position, that meant that numbers, if we ignore the kth number and the nth number, the other n minus 1 numbers, n minus 2 numbers, had to represent a legal derangement. Okay? And so I claim that the number of ways that we can build derangements, okay, of n, they are of 2 different flavors, and we can count how many there are of each flavor. Okay? And they're given by this recurrence. How many people understand what I mean? How many people don't quite see it? Okay? Just to sort of make sure that everybody believes. Let's go through this particular thing, and let's look at the flavors of derangements. Okay? Let's count how many fixed points we get if we did the swap. Okay? How many fixed points would we get if we did this swap? Okay? 2. This is one that, well, let's try this in different colors. This would be something that would be of 2 colors. How many if we did this swap? 1. How many if we did this swap? 1, because 3 would not be creating a fixed point. How many if we did this swap? 1. This swap here? 2. This swap here? 1. This swap here? 1. This swap here, 1. This swap here, 2. Okay? So we agree that if we look at this thing, there are 3 of these that represent double fixed points, and 6 that represent single fixed points. What we claimed was that d sub 4 should be equal to 3 times d sub 2 plus d sub 3, okay, where d sub 3 we said was 2 and d sub 1 was 1, okay? Any questions? Okay? So think about what that means, okay? It's a good example, again, of thinking about these things recursively to try to induce recurrences. Any questions? Question? Well, here we said the rule was we take the nth element, the largest one, 4, and figure out if we swap it back to its position, somebody else gets moved back into, we did a swap with the element containing 4 and the 4th slot. Either it's going to put 2 elements in the right position, like it does here, or it's going to put 1 element in the right position, which it does here. And we break down our permutations by that. Okay? Any questions? Okay. Anyway, this is sort of a classical problem in combinatorics. Okay, and like I say, in general, okay, that when you solve this recurrence, what you end up getting is something that approaches n factorial over e. Okay, and in fact, it approaches it very, very quickly if you actually sit down and compute such things. Okay, and that's why the probability would be 1 over e. I don't want to actually go and solve this now, but I just wanted to point that out. Any questions? What I did want to point out was a little bit of a kind of interesting combinatorial problem related to this, where we can start to use our notion of expected values we defined last time. Okay, is to think about how many fixed points you would expect. Okay, we'll say a fixed point, remember, in a permutation was a element such that the ith element in the permutation was I. A derangement had no fixed points. The sorted order had n fixed points. In general, what is the probability that if I have a random permutation of n elements, that I have exactly k fixed points? Let's think about it this way. Okay. Well, we can form a little bit of a recurrence with that. Okay, or not a recurrence, but using what we know, the probability that we get k fixed points can be determined as follows. Okay. Well, if we pick, how many ways are there to pick which would be fixed points? Well, we want exactly k elements out of n to be fixed points. There are n choose k ways to pick those fixed points, right? Okay. Once we know what the fixed points are, if we want to count all possible ways to end up with exactly k fixed points, that means the elements that we didn't pick had better not have any fixed points to it, right? And the number of ways to have that be done, once we've fixed which k we want as these things, is that we want that the other n minus k elements have to form a derangement. Correct? So my claim is that the number of permutations, okay, of size n with k fixed points is n choose k times the number of derangements of n minus k. Correct? That seems believable. And if you believe that, what's interesting is it gives us another way to count the number of derangements. Okay? How many permutations are there which have some number of fixed points? Okay, well, every permutation has some number of fixed points, right? So if we sum up over all permutations, there's going to be n factorial of them. If there are this many that have exactly k fixed points, if we sum up over all k, okay, from k equals 0 to k equals n, I claim every permutation has to be counted exactly once, correct? Every permutation has a certain number of fixed points in it. That number from 0 to n, summing up over all permutations clustered by fixed points, that has to be n factorial. Okay, how many people agree with that? Okay, that should be easy. Okay? So what's interesting is we can prove that therefore n factorial is the sum of these guys. Okay? And since we know that n choose k is the same as k choose n choose n minus k, we can make this n choose n minus k, then change the variable for n minus k. We basically have just proven a different recurrence for the number of derangements. That n factorial is equal to the sum of n choose k dk over all k. Okay? Any questions? Okay, so this gives a way to us to express, if you want to think of it, gives us a way to express d of n in terms of the number of derangements of all smaller things. And in fact, something about your series is that's sort of where the e is going to come out of, but we don't want to go through that. Any questions? Okay. What I ask you now is, just as a little practice for our mean thing, what is the expected number of fixed points we get in a random permutation. Okay, let's think about this thing. I now give you a permutation of length n. How many people on average will get their hat back? Okay. So now we're not talking about how many people, how many times, before we about what's the probability that nobody gets their hat back. Now let's say we do the experiment. Let's say that every one of you gives me your hat. Okay. Or since none of you have hats, let's say every one of you gives me your homework assignment. Okay. I scramble the homework assignments and I give them back to you in random order. How many of you are going to get your homework assignment back? What's the expected number of fixed points we get in a random permutation? Well, look at the following. F sub n we're going to define as being a random variable which says how many fixed points are there, okay, in a permutation of size. Okay, F sub n is going to be a random variable that operates on permutations that tells you how many fixed points there are. Okay? We want to know what's the expected value of f sub n. Correct? Summed up over all permutations. Well, one thing that we could observe is we could take a look at, represent the number of fixed points in a permutation, that random variable, as the sum of n separate random variables by saying what is the number of fixed points, okay, in this permutation in position I. Okay? So f sub n comma I on a permutation is going to tell us how many fixed points does that permutation have in position I. What's the maximum number of fixed points a permutation can have in position I? Well, 1, right? Element I could be right. Okay, and what's the minimum number of fixed points a permutation can have in position I? 0. This is a 0, 1 random variable, right? And my claim is the total number of fixed points is the sum of these random variables. Okay, correct. Well, what do I claim now? Okay, that if we want to think of what's the expected number of fixed points, okay, in a permutation of size n, my claim is that that's going to be n times the expected number of fixed points in the first position. Why is this? Let's think about this. First of all, I'll claim if we want to know what's the expected number of fixed points in the first position over all permutations versus the number of expected number of fixed points in the second position over all permutations, it should be obvious that they're all identical, right? There's not going to be more fixed points created in the second position than in the first position if you sum up over all permutations. How many people is this obvious to? Okay, how many people is it not obvious to? Okay. So I claim that the number of fixed points in each position, the expectation should be the same. So I claim the expected number of fixed points, we can say, is simply n times the expected number of fixed points in the first position. Right? Well, what is the expected number of fixed points in the first position if I give you a random permutation? Okay? I claim that there are n factorial permutations. How many of them are there with a fixed point in the first position? Well, if there's a fixed point in the first position, what is the element of the first position going to be? 1. How many ways are there to complete the permutation from then on? n minus 1 factorial. So what's interesting here is that the expected number of fixed points in the first position, okay, is 1 over n, correct? Therefore, since there's n positions in the permutation, the interesting thing is that the expected number of fixed points overall is 1. Okay? And looking at this, you should be convinced that this is independent of the number of people we have. That's the other thing that's interesting. The expected number of people getting their paper back does not change no matter how many people are actually turning it in. Okay? That's kind of interesting here. Okay? If you have one person turns in their paper, and I randomly permute it and give it back, what's the expected number of people getting the test back right? Well, 1. Okay? If I have 2 people, there's a 1/2 probability that none of them get it, and a 1/2 probability that 2 of them get it. So that works out to 1 here too. What's interesting here is that this probability is independent of the number of people, and that's the same property that will hold for the number of derangements overall. Any questions about that? Okay. So again, I think derangements are interesting things, and they're give us another chance to check out our ability to do recurrences, and a little bit of here to sort of talk about counting things using probability. Any questions? Okay. What I'd like to next talk about is, now that we're a little warmed up, is a really kind of interesting aspect of combinatorics related to probability. Okay? There's something that's kind of maybe probably the most important idea in combinatorics over the last 30, 40 years at least, okay, is the idea of what we would call the probabilistic method for combinatorics, okay? Combinatorics is mathematics of counting. Probability is the mathematics of flipping coins. It's hard to see how you can count things exactly by flipping coins, okay? But what's interesting about the probabilistic method in combinatorics is that sometimes you can prove certain things definitely happen, okay, by making an argument using probability, okay? And that's the idea of the probabilistic method in combinatorics. Okay, and I'd like to give you an illustration of the power of this, okay, by using a kind of famous problem in graph theory. Okay, any questions about what this means? It probably doesn't mean very much so far. Okay, but what I'm going to show you now is a way that we use probability to prove that something definitely happens. Okay, any questions? And the domain that I want to talk about is in an area of graph theory or combinatorics called Ramsey theory. Okay, why is it called Ramsey theory? It was a guy named Ramsey. Okay, that's what it's named after. Okay, and the way you hear this thing is, suppose, let's say, we have a complete graph defined on showing all possible relations between pairs of n people. If I have n people, okay, how many pairs of people are there on n people? There's n choose 2, right? Suppose these were people. Sometimes pairs of people know each other. Sometimes pairs of people don't know each other. Okay? Do you know him? No. Okay? Do you know her? She's next to you. Hopefully you know each other. Okay, well, let's say you know each other. Okay. Certain pairs of people know each other. Certain pairs of people don't know each other. Okay? And I claim that among any set of n people, there is a completely defined relationship between pairs of people that know each other and pairs that don't. Correct? Okay, and we can assume that you could have seemingly arbitrary structure to it, right? Either you know somebody or you don't. Okay, and you could have all kinds of different colorings. Okay, we can think of it a relationship between people as if they're friends, we'll color them blue, the edge blue, and if they're not friends, we'll color the edge red. Okay, it should be clear that any possible coloring of that represents a fair relationship. I have no constraints as to who can be friends with who. Okay, any questions? Okay. Now, what's interesting is, if you have 5 people here, I claim that no matter how you color the edges, okay, it's not necessarily true, okay, that you get a triangle of things the same color. Okay, what is a clique of people? A clique of 3 people, we'll say, are 3 people who mutually know each other, right? These are 3 mutual friends. And these are 3 mutual strangers. I claim if you have 5 people here it's not necessarily true that there has to be a clique of 3 mutual friends or 3 mutual strangers. Why is that? Well, the proof is in this drawing here, right? Here I have a possible friend relationship, okay? And, you know, friends and anti-friends. Is there a group of 3 people who are connected by mutual red edges? No, I don't see it, okay? Is there a group of 3 people connected by mutual blue edges? Don't see it, right? So it's possible you have a world where everybody's friendly, okay? But it doesn't have to be the case that there's a mutual triangle. Does everybody agree with that? The interesting thing I claim is that once you get 6 people in a room, you have to have a triangle of either red or blue, okay? No matter how you color that thing, okay? For 5 people, you're not doomed to have that. But for 6 people, you are doomed to have such a relationship, okay? No matter how you color it. Let's look at an example here, okay? I'm now just going to go draw numbers. 1, 2, 3, 4, 5, 6. Let's say I put there, 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 there. Anyone want me to put any other red edges? I'm going to put everything that's not blue that's not red. Who wants another red edge? Okay, you want a red edge? Boom, there's another red edge. Want another red edge? Let's put that there. Now it looks like we still don't have a triangle, do we? So far we have no red triangle, right? Is there any other edge I can go without creating another red triangle? I guess I could add this edge, right? If I add a red edge here, I've got a triangle, right? Red edge here, I got a triangle, right? Red edge here, red edge here. Now suppose I fill the thing. So there's no red triangle, is there, right? But what if I now connect everybody by blue who's not connected? Who's not there? Has to be a triangle there, right? So the amazing thing is that no matter how you color, okay, a set of seemingly you can have arbitrary relationships between people. You're allowed to make friends with whoever you want. And yet somehow, once you have enough people in a room, okay, there has to be certain structures present. Okay? That's really the amazing thing about Ramsey theory, is it says that even in worlds of complete disorder, there has to be certain amounts of order. Okay? And so I claim that once you got 6 people in a room, you have to have either 3 mutual friends or 3 mutual strangers. I was going to say enemies, but that's not right. Strangers. Okay? Any questions? Okay? So what is this called? Well, in general, we'll define the Ramsey number, KK, is defined as the smallest number of people you need, such that in any friendship graph on that many people, you have to have, okay, a monochromatic, complete graph of K. Okay? A triangle is a complete graph of 3 things, right? What's a complete graph of 4 things look like? All 4 things have to be related to each other. So the fact that the Ramsey number 3, is 6 means that once you have 6 people, any red 2 coloring of the edges of 6 people have to have at least either a red triangle or a blue triangle. Once you have 17 people in the room, you either have 4 mutual friends or 4 mutual strangers. Okay? In here right now we have probably somewhere between 42 and 55. Okay? It's been proven that the Ramsey number, I think actually it's been tightened since this now, but basically if we have more than 55 people in the room, okay, then either there's 5 people in here who are all mutual friends, or 5 people in here that are all mutual strangers. Okay, and these bounds are Ramsey numbers. Any questions about what we mean by Ramsey numbers? Okay, it's an interesting thing. Now, finding, here if you notice there's some uncertainty. At the time I made up the slide, no one knew whether the exact number of people you needed was 55 or maybe 42 would be enough. Okay? Finding the number of people you need to ensure a Ramsey number, okay, ensure that you've got these monochromatic sets, is a famous, difficult problem in mathematics. Remember one of the authors of our book is Ron Graham. He was the juggler when I showed you the pictures. His car, his license plate reads Ramsey. Okay, he's into Ramsey theory. Okay, and he was so excited he got a license plate for it. Okay, so it's very difficult to prove exact bounds on Ramsey numbers. But what I'm going to now show you is a way to prove that the Ramsey number is bigger than something. I'm going to prove a lower bound on the actual Ramsey number. Meaning that if I want to guarantee that, I have a set of K mutual friends or strangers, I better get at least that many people in the room to guarantee it. Okay? Any questions? Well, let me now show you how to prove this using an argument about probability. First of all, any questions about Ramsey numbers? Like why, what this is about? Or any questions about the definitions? Okay? Suppose I now take a set of n people, okay, and build their graph on them by randomly flipping a coin, okay, to decide whether or not the edge is blue or red. Okay? If I do this, you'll certainly give me that I can take for any n, this gives me a way to color the graph, right? Randomly pick things. Suppose I do that operation. Suppose I give you a graph, n people, let's say I randomly flip coins, 1, 2, 3, 4, 5, 6. Suppose I randomly flip coins, that's a head, that's a tail, that's another tail, head, tail. By doing this, I will eventually fill in the entire graph, right? I'm maybe missing something, but let's not. Okay. Now I take a look at this thing, and I ask myself, here is a subset of 1, 2, 3 things. What is the probability that if I flipped coins for each edge, what is the probability that this would represent a monochromatic triangle? Okay, for this case of 3, look, it did in fact do that. What is the probability that if I pick the edges randomly, what is the probability that they all come up to be the same color? Okay? Okay? How many ways are there to flip edge? If I think about it, there's 3 separate edges. How many coin flips are involved? 3 coin flips. There's 8 outcomes to the coin flips, right? How many of them leave the thing the same color? 2, right? Because I could have flipped them all head, head, head. Could have flipped them all tail, tail, tail. Okay? So my claim is that in general, okay, the probability that a given subset of size k of k vertices is monochromatic after I've done the flipping is, I claim, 2 over the number of edges in that subset, defined by that, which is 2 to the k choose 2. Okay? How many people agree with that? How many people don't see what I mean? Okay, any questions? Okay. So this says, what is the probability that it was monochromatic? Okay. Now, in general, how many subsets of k of the vertices, if there's n vertices, there's a total of n choose k subsets of those vertices, right? So what I want to now determine is, if I flip this coin, if I randomly colored the graph, I'd like to determine something about what's the probability that I get a monochromatic subset? Okay? Now, suppose I want to ensure to find the probability that none of them is monochromatic. Okay? The probability that A or B is true, I claim, is the probability that A is true plus the probability that B is true minus the probability that both of them is true. Correct? Does everybody agree with that? Okay. This is where we really get into issues of independence. Okay. Suppose the two variables are completely dependent upon them. Okay. Let's say that if one of my eyes, let's say everybody has the same color eyes. Okay. One eye is the same color as the other one. Okay. What's the expected number of blue eyes I have in here? Well, the probability that I have both a left eye and that either this is true or that is true. This is blue or that is blue. Okay. Well, in that case, the probability that both of them is blue is the same as the probability that one of them is blue. So then here the probability of this, with A and B, would be, the bigger it would be the same as 1, and it would just be left with the probability of one eye. Okay? If these were two independent random variables, what's the probability that both A and B were true? It's the product of those two, right? Okay? So this could vary pretty wildly. It could be smaller, it could be, and if they were opposite things, this could be 0. It could be like, let's say, if this is a probability, if this is heads and this is tails, they can't be mutually both heads and tails. So this could vary a lot. Okay? But what if I want a bound on this probability? My claim is that by dropping this term, I know that the probability that either of these things is true, that at least one of these things is true, is less than or equal to the probability that both of these things is true. Okay, does everybody agree with that? Okay, that's good. So what do we know about the probability that if I I do a random coloring of a graph, okay, on n vertices, what is the probability that I get at least one monochromatic triangle? Okay? The probability that a monochromatic K, complete subset of size K. They're all told this many different subsets. Okay? The probability that I get at least one of them, okay, as being monochromatic is the sum of the probability that any of them are chromatic. Right? This, I claim, has to be bigger than, greater than or equal to, the probability that there is a monochromatic one. Okay? It ignores the fact that it double counts the fact that maybe I'll get more than one. Okay? So my claim is the probability to get a monochromatic K subset is at most this. Okay? How many people agree with that? How many people are confused? How many people are losing thread of the argument because it's getting kind of long? Okay, a couple people. Okay? But we're almost there. The probability, therefore, if this is the probability that there is a monochromatic K subset, 1 minus of that, okay, the probability that there does not exist, okay, a monochromatic K subset is 1 minus that, right? And so if the probability here was at most this, 1 minus this is at least that. So I claim what I've just proven is that the probability that there does not exist, if we randomly color the graph, the probability is that there does not exist a monochromatic K subset is at least this. Okay? Any questions? Well, what's the big deal? Well, let's think about this thing. Suppose it's the case that this is less than this. Okay? 1 minus something that's less than 1 is what? Something that's bigger than 0, correct? So suppose this is less than 1. That means that the probability that there does not exist a monochromatic K subset is greater than 0, right? Okay? Let's think what that means. Suppose, let's say that I have n and k such that if I randomly randomly flip the coins, the probability that there does not exist a monochromatic K subset is greater than 0. What does that mean? If I flip the coins again and again and again and again and again, eventually I will end up getting a monochromatic K subset. Do you agree? Suppose the probability is, let's say that the probability that I don't have it, okay, that there does not exist a monochromatic KK. Suppose that this probability is greater than or equal to 1 over a million. Okay? 1 over, I know it's not, let's say 1 over 100,000. Okay? If I flip this 100,000 times, okay, will I get a monochromatic K subset? Okay? Well, quite probably. Okay? If I flip it 1 billion times, will I get one? Well, eventually, if I flip it enough times, I'm going to get one, right? Well, what does that mean? That meant that there had to be one for me to get, right? If, in fact, by flipping the coins, the probability that I get such a monochromatic subset, K subset, that there was a way to color it, such that I did get such a subset, okay, meant that there had to be a coloring, okay. Wait. This is the probability that there does not exist such a one is at least this. That means that with some probability, I am going to get one, right? Okay? If I can get one, that meant there had to be one there to be gotten. Okay, this is sort of the punchline. Okay? If their probability is non-zero, there must exist such a coloring with a clique. Okay? And that meant that the Ramsey number, remember, said that if saying that the Ramsey number for k greater than n meant that I had to have more than n vertices so as to guarantee the existence of a monochromatic thing. That's what the Ramsey number meant. Okay? This is the probability that for this n and k, I don't get a monochromatic thing. Okay? If the probability that I don't get a monochromatic thing on a random coloring is greater than 0, that meant there had to be a coloring where there was a non-monochromatic thing, right? If there was a probability of greater than 0, that meant there had to be at least one of them. The Ramsey number says I have picked a large enough value of n such that no matter how you color it, you're going to have a monochromatic thing. The fact that so long as this thing leaves me with a probability of greater than 0, it means that that n is not large enough to guarantee the Ramsey number. And so what's interesting here is I can use this to prove a bound on how many vertices I need to guarantee the existence of such a thing. Okay? How many people sort of see the reasoning? How many don't? This is confusing. It's fair to say you don't. Okay? How many people don't? Okay? No one will admit to that either. Suppose this is true. Let's think what this means. Okay? We're interested, I claim, is under what condition is this going to be, we're worried about, so long as this thing is greater than 0, something bad happens. So where is this thing equal to 0? Well, it's when this is equal to 1. Under what condition is n choose k over 2 to the choose k minus 1 roughly equal to 1? Well, n choose k is roughly n to the k. If you stop and think about it, that's right. It's some other things being divided by it. But it's basically n times n minus 1 times dot, 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 roughly n to the k. 2 to the 1 minus, okay, k minus 1, 2 to the k choose 2 minus 1. 1 over that is the same as 1 minus k choose 2. This I claim is roughly 2 to the k minus k squared over 2. Saying that we want this ratio to be about 1 is basically going to be true, okay, when we have this thing equal to, basically when n is, we solve for n, what do we do? If we want this to be equal to 1, we multiply both sides by the 2 to this thing to get rid of the denominator. Take the kth root to get rid of the exponent. This tells me that n is roughly going to be equal to 2 to the k squared over k over 2. The k squared over k, one of those k's canceled. This, I claim, proves that the Ramsey number, okay, for a given k has to be greater than or equal to 2 to the k over 2. Any questions? The algebra here is not that interesting, okay, but I've just finished doing that. The interesting thing is the probabilistic argument. Okay, so let me just go through that one more time. Okay? We are going to figure out what is a Ramsey number. A Ramsey number is a number of vertices that says no matter how you color this thing, you're going to get a monochromatic k-gon whether you like it or not. That is what the Ramsey number is. It says that I have an n large enough to guarantee me on any coloring there is a monochromatic k-gon. Correct? Well, what have we done? I've proven to you that if you randomly flip a coin, okay, to determine the colors of each edge, okay, with probability, there will not exist, okay, a monochromatic set in that. Question? K-gon meaning complete graph of K, not a K polygon. I slipped that. I was hoping to avoid that, but you caught me. Okay? What it means is a Ramsey number is a sufficiently large number to guarantee me, the Ramsey number K is enough to guarantee me that there will not be there will be a monochromatic k-gon. Correct? K complete subgraph of size k. Okay? Now, suppose, let's say, that for this value of n, okay, well, basically what I've proven is that for a given value of n in k, if I randomly color the thing, the probability I do not get such a thing, do not get this event, okay, is this, at least this. Okay? If this is greater than 0, that means that there had to be some way to flip the coins such that this event actually happened. Okay? If there was some way to flip the coins such that there does not exist a monochromatic k-gon for n, then that meant n was not big enough to guarantee me the existence of such a thing. Okay? And so therefore n has to be bigger than that to make that guarantee. Okay? So the interesting thing is that this probabilistic argument proves definitively, without a shadow of a doubt, that the Ramsey number for a given k is greater than or equal to 2 to the k over 2. Okay? And we're using a probability argument to show that. How many people sort of get it? Okay? How many people don't get it? Any questions? Okay? Again, this is very, very interesting idea, this linking between proving the definitive existence of it through probabilistic arguments. Okay? And like I said, this idea of using the random method for doing counting is probably one of the more important methods developed in combinatorics over the last, I would say it's really been developed since 1960. Okay? It's an interesting idea. Any questions? And I urge you to go through it at some point just to check to make sure that that actually works. Any questions? Okay, what I'd like to do now is to give out the exam. Okay? I want to go through it quickly just to sort of make sure we understand this thing. Okay, let me pass these out. And why don't you guys pass this, pass this, pass this. Okay, I want to pass these out among yourselves. What I want to do actually is just quickly talk about, actually, can I borrow somebody's? I just gave away my copy. Let me borrow somebody's for now. Okay? Let me just go through quickly what the questions are. Okay? This is going to be due over it's due the Tuesday we get back from spring break, so you have a little over a week. You have a weekend, closer to 2 weeks, I guess. Okay? But I did try to make the problem, I think, shorter. I think the problems are easier than before. Okay? We'll find out if that's true. But I believe that's true. So I urge you to take a look at the, for those at Ademco, this will be on the web soon. Okay? If it's not on the web by the time you come home, by the time you go back to, but by 5 o'clock, keep giving me phone calls and email. I will get this on the web. Okay? Please keep after me on that. Okay? But there's 6 problems here. I urge you to take a quick look, read through the exam a little bit now, just to see if there's any particularly outstanding questions. Okay? Because next week is spring break, and I will be gone over. I'll be gone over spring break. I'll be reading my email, but if there's any questions, now might be a good time. Any ambiguities, now might be a good time to look at it and review that. Okay? So maybe I'll give you back your test so you can review ambiguities. Are there any extra copies of the test? Let me get one of those. Look at it quickly. Ah, here we go. Good. Okay. You need another one? Sorry about that. Okay. Okay. Any questions? Okay, questions?
For number 2, when you said evaluate the following sum, like you can use any method that we learned.
Right. So basically, I want you to go and show me what S sub n is. Okay. You should figure it out and convince me why that's true. Okay. So your method should not just be guessing and but you should show me why that's true. Okay. So give me a formula for what S sub n is. That's really what I'm asking for. Okay. Any other questions that come to mind? Okay. Give people another minute to read. Any obvious ambiguities or anything like that? Okay. What I'd like to do is, again, so basically this is going to be due when we get back. Now, one thing that I'd like to just make an announcement related to this that may have some impact on this thing. I wanted to, after thinking about the last exam and how much time it took and how much time people spend on this and all this kind of stuff, and various things about it, I made a decision to do a little bit of a change to the grading distribution. Okay? And so I want people to know about this before the exam. Basically, I decided to take a little bit of the credit away from the take-home exams and put it more on the final. Okay? So basically, before it was 20% on the 2 take-homes. I'm moving that down, so I'm making the take-homes worth less than they were worth before and putting more on the final exam. Okay? So this may be something you'll keep in mind when you figure out how much of your break you want to ruin for this. Okay? You shouldn't be willing to ruin too much of your break. Okay, as much of your break for this as you would have otherwise. Okay, that's sort of an important point to see. Okay, I don't want anyone to ruin their break. My hopes are that, again, do the best you can. Okay, my hopes are you can. I give some hints for some of these that should make it easier. Don't expect to get 100, so don't ruin your break for that. Okay, but give it a shot. I think some of these are interesting. A couple of them are not so hard. Some of them, I don't think there's too many that are really, really hard. Okay, but if I'm wrong, don't ruin your break over it. Okay, do the best you can. But anyway, take care. Good luck. See you guys later. Thank you. Yeah. Okay, great. Thanks a lot. Yeah.